if you're new to this format, essentially what I do is usually every week on Saturdays at 10 a.m. Central Standard Time, I stream live. And what I do is all of the topics that I have are viewer generated, and then they have a poll and they pick what it is that I talk about every weekend, and I throw together a little bit of information, and then I also give you additional resources to where you can find it. All the slides on my show I post on my website, scientistmel.com, so you're able to go there and do some more further research and kind of see what it was that I was talking about, as well as my original sources. So let's go ahead and get started. So today we are going to talk about HIV, history, and immunity. First thing we have to do is talk a bit about what it is. So what is HIV in general? It's the human immunodeficiency virus. And what that means is it's the virus that causes AIDS, also known as acquired immune deficiency syndrome. It's a virus that attacks the immune system. So what we have over here in this picture is like a cartoon of HIV. It's this little round globular looking thing. It has all of these little what look like feet on the outside of it called glycoproteins, and that's its mechanism of how it attaches to other cells. Now on the inside we have here our RNA strands. And these RNA strands, if you're unfamiliar with cellular biology, ribosomes read RNA strands and they make proteins associated with it. So the other thing that we find in this particular virus is what we call reverse transcriptase. I'm going to talk to you about how it actually infects a person, as well as what it actually does on the inside of these cells and what kind of cells it attacks, and a little bit about the history of HIV. So let's have a look at the mechanism of how it enters a cell. So, let's go back. So HIV primarily infects cells with something that we call a CD4. Why is it not going back? It doesn't have my fancy image. So what it has here is on the outside of this is a CD4 cell receptor, and it attaches to these particular T cells, and that's how it gains entry. Now, many types of cells share this common protein on the outside of it through what we call CD4. So if you're unfamiliar with receptors, let me give you a really quick sum up of what it is. On the outside of cells, if you look at HIV here, these are all like little antennae. And so these little antennae that are on the outside of this HIV virus attach to what we would call antenna kind of cell receptors on the outside of our immune cells, and then that's how they connect, kind of like a puzzle, and then that allows HIV to enter inside the T cell with all of the stuff on the inside, the bad icky stuff, that RNA transcriptase, all the stuff that kind of screws up our immune cells, that's on the inside. So that's how it attaches, and then it allows passage into the cells, into the T cells. Now, there are some cells that don't have those particular receptors, but they have slightly different ones. So sometimes, like macrophages and fibroblasts, if you check out my vaccine video, you'll see that I talk a bit about those particular cells in the first immune response and the second immune response. So HIV attacks the highly specific secondary immune response, the ones that we normally get vaccines for, because the first immune response isn't good enough. It has to be highly specific because of all those antennae on the outside. They're different on certain viruses, and so that's what we vaccinate against. But HIV changes a little bit, so that's what makes it hard. So let's look at, I'm going to pop over to this. So I'm going to show you which immune system cells that they attack. So these particular cells here, this is part of our secondary immune system. We have T helper cells, we have B cells, we have killer T cells. So what we see, HIV primarily attacks T lymphocytes, B cells, natural killer cells, lymphocytes, dendritic cells, which are like part of your brain. Those are called Langerhans cells of epithelial and follicular dendritic cells, are also in lymph nodes. They attack hemopoietic stem cells, endothelial cells, microglial cells, gastrointestinal epithelial cells. All of these are primary targets of HIV infection. So any of those cells that have that CD4, you notice that little CD4 receptor, if they have those CD4 receptors, they could very well get infected by HIV. So let's talk about what happens when it sticks to it. All right, don't get freaked out by this picture. I'm going to explain everything to you. Some people are like, oh my gosh, all these letters, what are they? All right, there's some important information here. So we're going to look. I've got my little pointer here. Here's an HIV virus. All right, it binds to a host cell. Here's the CD4 receptor. Well, guess what? I'm going to talk about immunity here today, and it has to do with this, what we call a co-receptor. So HIV tends to need two different things. This little co-receptor here that's on the outside of our T cell and our CD4 receptor, so it kind of hooks up and attaches and kind of holds it in place, kind of like a rope. And then what happens is that RNA that helps make proteins leaves the HIV cell and enters into our cells. All right. Now what happens is RNA is kind of usually falls apart inside a cell after a while. But there's this little enzyme called reverse transcriptase, which turns RNA into DNA. Now that's a big freaking problem because DNA is highly stable. And then we get something called integrase, which incorporates that DNA into your cell. Sorry, let me go back. I didn't mean to click. So it goes into your cell and it gets incorporated into your genetic makeup. It actually gets put into the nucleus of your cells. That's why they say if you get a retrovirus, you have it forever because it gets incorporated into your DNA. So what happens then? Well, it then starts making virus RNA, and all your little ribosomes that normally would make T cell types of proteins are now making HIV type of proteins instead of making T cell proteins to make your immune system do its job. So once an immune cell is infected, HIV takes over everything and it starts only making HIV proteins. So then they leave the cell in these little bubbles and they make brand new virus particles. So that's what makes HIV so awful. It attacks the very thing that is needed to fight it off. So what I'm going to do now is talk to you a little bit about, let's see, about the history. I want to talk to you a bit about the history of HIV, and we are going to start with 1981. This was the very first recorded appearance of HIV, and what was happening were people, primarily men, were coming into clinics with very bad cases of pneumonia, and they also had something called Kaposi's syndrome. I think I spelled that wrong. So what happens is that particular sarcoma is like a skin type of cancer where you have purple spots on yourself. And so you don't normally have that if you have a functional immune system. And they saw that these individuals had an immune system that wasn't functioning at all, and they were dying from very rare diseases. And they're like, what is going on here? We hop to 1982, and we see that the first American AIDS clinic was founded, and congressional hearings started in response to this particular disease. The CDC at the time estimated that there were tens of thousands of people infected by this strange disease that they didn't quite understand. And already they saw 22 cases of infants infected that were kind of rare. Now, in regards to the congressional hearing, that was on April 13th, U.S. Representative Henry Waxman convenes for the first time to discuss that. And so these babies that were infected, they didn't quite understand. They were like, why are these babies infected? And that's when they started to kind of connect, oh, there's blood transfusions going on here. So that's when they kind of started taking notice about that and tried to develop a test to try to detect it. Now in 83 and 84, the U.S. Congress passes the first bill that includes funding for specifically targeted research in regards to AIDS in treatment, about $12 million. That's not a lot in our time, but back then, that's kind of what the initial funding was. But clearly more money was needed. And so the 12 million was dispersed amongst agencies within the U.S. Department of Health and Human Services in 1984. And that's when they started understanding AIDS can be cured. Well, they're working on that, and I'm going to talk about that special kind of immunity that certain people have, and that being a possibility of exploration. All right, so in 1984, that's when they started noticing that needle sharing amongst drug users became an issue and a possible mode of infection. 1985, I don't know if you're familiar with Ryan White. He was one of the first people that came forefront about the blood transfusion. And I lost a bit of my second bullet point. He was an advocate essentially for education. An advocate for education as far as trying to get people to understand HIV infection. He was denied entrance into his middle school because of his infection from a blood transfusion. And so he was kind of trying to get people to understand, when he was little, he was a middle school kid, but everybody was so afraid that this was some kind of contagious, type of disease. And so he became an advocate for education in regards to that. And then in December 6th of 1985, the CDC started recommending different protocols to kind of put into place in order to protect babies, and mother-baby transmission was becoming a possibility. So that's when they started exploring that. 1985. All right, the next 3 years I'm going to talk about. We're moving through this as quickly as I can. This is kind of substantial because in 1989, 100,000 cases were reported. By 1992, it was the #1 cause of death for men in the United States between the ages of 25 and 44. Then, in just 2 years, this disease became the #1 cause of death for all Americans between the ages of 25 and 44. So we jump from 1981 to 1994. It became the #1 cause of death for anyone between the ages of 25 and 44. So that's pretty substantial. And it's really, really kind of scary. And then in 1994, AZT, which is a drug that kind of stops that RNA from being read by ribosomes making HIV proteins. You remember I talked about the mechanism? AZT stops ribosomes from reading HIV code, okay? And it stops that from being that reverse transcriptase. I believe it's the reverse transcriptase that keeps it from turning it into DNA to be put into the nucleus. I need to go back and look at that for you. But AZT essentially stops those proteins from happening in that way. And I believe it's with the reverse transcriptase from stopping it from turning into DNA. It's been a while. And some strains of HIV are resistant to AZT now. They've developed they've evolved. So HIV actually can evolve, and that's one of the things that can become resistant to certain antiretroviral medications. And AZT they started giving that to pregnant women to stop transmission between them and their babies. I will double check that mechanism on AZT though, and I will report back. All right, now let's talk about 95, 96, 97. All right, so in 95, we're up to 500,000 cases of HIV infection reported. And then they started in 96. They were like, all right, we need to start working on a vaccine. So 15 years later, they finally start working on a vaccine because it's become such a massive issue. And so the International AIDS Vaccine Initiative forms. Now this is around this time, I believe it was in 1997, the year right after that, they had the first HIV home test as well as a viral load test. If you're unfamiliar with a viral load test, what it does is it determines just how much of the virus is present in your body at any point in time, because that kind of gives you a good idea of your level of progression, of how far you are in regards to infection. Because if you're able to keep the viral load down, you can minimize your symptoms and minimize that amount of HIV that's attacking your immune system. Because essentially what happens is when your immune system is attacked, you don't die of HIV, you die of all of the diseases that attack your body and cause you to be incredibly ill. You don't get better. It just keeps all these different viruses and bacterial infections do you really a lot of harm. So they came up with the viral load test, the non-nuclease reverse transcription drug, Nevitapine. I don't know if that's how you say it. So they start developing essentially new medications to kind of stop reverse transcriptase from incorporating that RNA, turning it into DNA and putting it in the nucleus. And then they came up with Combivir. I don't say words right sometimes. And that's a combination of two different antiretroviral drugs in the hope that if the HIV was resistant to one, maybe it wouldn't be resistant to the other. So they started a battery of several antiretroviral medications in order to try to stop that viral load from increasing the amount of HIV in your system. That's kind of what those do, is to kind of minimize it, making more copies of itself. All right, we're almost done with the history. All right, so we jumped to 2002. It's now become the leading cause of death for people in sub-Saharan Africa. And we start to hear reports in dozens of other countries where it's a serious epidemic. Then in 2003, the government, in addition to other private organizations, including the Gates Foundation, start contributing to AIDS research, including medications as well as tests and possible viruses. So for as much flack as people give Microsoft, Bill Gates is responsible for a lot of HIV research in regards to moving forward to the point now we're currently testing a vaccine in Africa, and I'm going to talk about that. Then in 2007, the CDC reports that 565,000 people are dead from AIDS and from AIDS-related illnesses since 1981. So this is a pretty substantial thing that's taken a lot of lives. So here we are towards the tail end. This is why ACA is important. And so I'm going to kind of say this. The Affordable Health Care Act that's constantly being battled against. In 2010, they extended coverage to people who suffer HIV as well as other types of diseases, including types of cancers where they normally would not get health care for. So in 2010, the ACA extends coverage to those individuals, which would normally be excluded from health care. In 2012, a new drug is developed called Truvada. It's a pre-exposure prophylaxis type of medication where people who don't have HIV but are at risk for infection can take it preemptively if they've possibly been with a person who's HIV infected. This could be in cases of rape and that sort of thing, where individuals were exposed. They can take Truvada to limit their risk of infection. So that's the first time that this drug has been developed, and it's still actively used. Now, the good news, since the implementation of what we call PEPFAR, that's the President's Plan for AIDS Relief. For the President's Plan for AIDS Relief, since that was implemented, more than 1 million infants have been born HIV free. So we know that we're able to stop, or at least limit, the chances of a mother transmitting the virus to her babies. So yay, science on that. So the last bit on the history, 2014, that's when the first phase of partner studies began. So what essentially they were trying to do was look at the rate of transmission and the transmission risk between partners, one who had HIV and who was not affected. Now in 2015, infections fell by 19% since 2005, and that's pretty substantial. There were steep declines among heterosexuals, people who inject drugs, and African Americans, especially Black women. Now, the trends for gay, bisexual men varied by race and ethnicity. So what we're looking at is that the antiretroviral therapy in regards to this is highly effective for treating HIV. So this is, and also preventing sexual transmission of HIV from a person living with HIV to an uninfected heterosexual partner that was HIV positive. So those partner studies kind of played out, and we saw that these antiretroviral medications are working. Those pre-exposure ones are working to kind of keep transmission from occurring. And now, in 2016, all right, there's a new clinical trial that's based in a vaccine focused in sub-Saharan Africa, where the international study shows that since we've got this problem, now we're seeing an increase in resistance with some of these antiretrovirals, and so there's a lot of work to try to come up with new medications and of antiretrovirals for those who are infected with HIV to kind of keep the viral load down. Now, the National Institute of Health partners announced that they're launching, and this was in 2016, they launched a large HIV vaccine trial in sub-Saharan Africa starting in November of 2016. And so what they're hoping to do with this, and what I'm going to talk about, is this. I didn't delete the bottom. The experiment, essentially. All right, so what I'm going to talk about. The experiment, essentially, this regimen is based on the U.S. investigation by the military for the HIV research program associated with the RV-144 clinical trial. And what they found is the current regimen is kind of designed to mirror that with this new vaccine trial that was adapted to this subtype, because there's several subtypes of HIV, and the particular subtype that's prominent in Sub-Sahara is a little bit different than in other places. And so they adapted this particular regimen for that exclusive type of HIV. Now, this regimen was found to be effective in the military studies, to be around 31.2% effective in preventing HIV infection during the first 3.5 years. Now they found that in the first year, it appeared to be 60% effective. So what's happening there is they need to shift the regimen a little bit to where possibly more introductions of this vaccine. If you watch my vaccine particular talk, sometimes you need multiple doses in order to increase the immune response. So what they're doing is they're adjusting the new study and schedule of the RV-144 vaccine to where it can be optimal in increasing the immune response and immunity duration. So the National Institute of Allergy and Infectious Diseases is overseeing the operational aspects of this trial. Now, this is going to include 5,400 HIV uninfected men and women ages 18 to 35 that show a substantial risk for HIV infection. Now, the NIAID, that's the National Institute of Allergy and Infectious Diseases, they funded this HIV vaccine trial network, and the HVTN will conduct the study. Now, the exciting thing is we'll see these results in about 3 years. They're expected to be late 2020 when we'll see these particular results. So, what I want to talk about now is the mode of transportation or mode of infection, and I want to talk about immunity. So here we have a little GIF image. That's HIV that looks like a bouncing bubble there. And so what we know is, and I showed you earlier on the mechanism on that big scary slide with all those letters and stuff, we have the CCR5. You remember I talked about CD4 being a receptor. Well, it has to have that CCR5 that kind of look like a rope to kind of holster the HIV and bring it to the receptor. So HIV needs that co-receptor for that entry. So that CCR5 works like a little lasso and it latches onto the HIV and it holds it into place and brings it to that CD4 receptor. Now, some people are resistant to HIV because they lack that CCR5 little rope co-receptor that lassos onto the HIV. And this is through a mutation in the gene that expresses that receptor. Now, what happens is that HIV then doesn't really attach to the T cell. Therefore, there's no infection. It can't enter into the T cell if it's not brought down and attached to it. But here's the thing, CCR5 is not the whole story of immunity for HIV. Some people resistant have found to have perfectly good copies of the CCR5 gene, perfectly normal copies, but still are resistant to HIV, which kind of leads to the thinking there could be other genes that contribute to slowing or stopping HIV infection. So there's current research going on about that. So it's kind of exciting stuff. So I want to kind of go back over, that's where immunity was. I want to kind of go back over a little bit from what we've learned. HIV, the human immunodeficiency virus, that's the virus that causes AIDS. HIV doesn't kill you per se. That's not what causes your death. What causes your death is the immune system being eaten by HIV, essentially converted all the T cells into little manufacturers of HIV. Then, once all of that is suppressed, your body gets bombarded by all kinds of secondary infections, the flu, pneumonia, leukemia, that sort of thing. On a side note, in regards to something that's incredibly interesting about the CCR5 gene, the CCR5 gene, how they found that out was through a bone marrow transplant, and the studies were the findings were published in Nature in 2009. So that particular gene they discovered that was missing in an individual who was donating marrow to a patient who was HIV infected and suffering leukemia. They know bone marrow transplants have been effective in helping people, fight off leukemia cancer. So what they found is that 20 months later, after doing this bone marrow transplant, the HIV infected patient was completely cleared of the virus in 20 months. So that's how they were able to find these immuno-resistant individuals to HIV. So that's a lot of studies associated with that. So that's kind of a cool little story. It's completely found by accident. But it's pretty awesome that we know that. So immunity exists, There's new trials of vaccines that are happening right now. We'll have the results for that for 2020. And hopefully, if they're effective enough, even if it's only 60% effective, that's still better than nothing. That's still better than 31% after 3.5 years if they're able to give booster shots for that. So there is hope. It's not necessarily the death sentence that it used to be. And we know that education and lowering risks reduces the infection and thus works. So it's not as bad as it used to be, which is a good thing. So I want to show you all of my sources. If I can get to it, here we go. And I'll post these on my website so you can go and check out and read for yourself. So the very first source where I got all of my information, they have way more information on hiv.gov. You can learn all about the history of it, involving everything associated with the world. It dates from 1981 to 2016, every single year, with every bit of information. The large-scale trial that's launched in South Africa is on nih.gov. You can check that out. There's a tutorial on utah.edu where you can learn about AIDS and the tutorial associated with how HIV becomes AIDS. Then if you want to learn more about the CCR5 gene, genetics.thetech.org, fantastic article there. And then nature.com has the particular article associated with learning about the CCR5 gene mutation. So you can find me pretty much everywhere on the internet. Scientistsmell.com is my main site. So if you can't remember all of my Patreon, Periscope, YouTube, Facebook, it's so hard. It's all Scientist Smell. But if you don't want to remember that, just remember my name, scientistsmell.com. You can find all of my slides there. You can find my articles there that I write. You can find my podcast. My Hey Scientist Smell podcast is on there as well. There's an RSS feed. I'm writing right now on new kinds of articles. I come out with an article once every few weeks. Probably do more of that. So check it out. And also, if you're an educator, all of my slides are available there. So if you like this particular show and you need some content for your classroom, just go to my website. I also have slides there associated with when I used to teach. So that's all available for educators to use. You're welcome to use it in your classrooms. You know, it's kind of what I do. So I enjoy this. So I'm going to take a moment to thank all of my patrons. I've picked up so many more patrons now. And some people have sent me donations through PayPal. So if you can't commit to monthly and you just want to chunk a little bit at me to try to help me keep things going, you can DM me, send me an email, and I can send you my PayPal information. So thank you to my patrons, Tony, Lauren, Anonymous, somebody's doing Anonymous, Mark, Jen, Carl, Anthony, Paula, Zachary, Carrie, Keith, Patrick, Tony, Tristan, Jennifer. Lauren actually paid through PayPal, and she gave me a substantial donation. So I will always give you a shout out if you even send me something on PayPal. So thank you guys for helping me with that. And this has been the science of HIV, history, and immunity. This is how the mechanism is, and this wasn't working on my other slides. Technology. But there you go. And if you have any questions, you can always ask me here when I'm streaming live. And if you didn't get a chance to interact with me here, that's okay. You can hit me up on Twitter, send me an email. I'm on Facebook, and I will answer your questions to the best of my ability. So thank you guys for hopping on here. This has been pretty awesome. And I guess I'll see you around on social media. Sending squishy science hugs. Have a fantastic day.